conformal class.
Yeah.
I mean, there's no real grade.
Yeah, a lot of
Nobody
things.
really care. Everybody has.
All right. Should I deliver this to you?
I will pick up my computer in maybe to your from your office.
Okay. I'll keep it down there. If I'm not there, I'll just put it on my desk.
Okay. When should I start studying for the final?
There's no file. Nice big function.
Actually, because of the chairs are in front of me. They're usually not that hard. So that camera is pretty
I will show you how easy it is.
Yeah, it's super easy.
Okay, so for the next essentially remainder of the quarter, I'm going to do some renormalization group calculations in actual interacting models. And of course, you know, the general way of doing this is by perturbing methods. So since I'm being filmed, I will tell you a joke, which of course otherwise I would never do. And that is this some dark street, and there's a policeman walking by, and he runs into a drunk, and the drunk is on the floor looking around and so on and so forth. Under a street lamp, and so the policeman says, what's going on? The drunk says, I lost my keys, I can't believe it. And the policeman says, well, where did you lose your keys? I lost them way out there. So why are you looking here? Because the light is better here. You must know this joke.
No.
Well, in some sense, it's not entirely a joke. This is, in fact, a deep statement which is related to because basically, the idea is that, well, perturbation theory is around a model or a theory that you know very well, often free field, but it doesn't have to be. And so in the neighborhood of this theory, one can explore the renormalization group and look for other fixed points. If you don't have something like that, it's very difficult to go find your key, or in this case, your fixed point, somewhere else. If you don't know that there is some sort of fixed point, it's very difficult in general. So the only methods known are, in general, if you have some way of solving the theory exactly, okay, and or predicting at least the existence of a fixed point exactly, which is in general extremely difficult. So instead, what one has is there is some known fixed point. Okay. And now basically you go in a neighborhood, and this neighborhood is in a space that's actually the space in some sense of all theories, of all operators that you can have. And you look in this space and see whether by any chance there is another fixed point here. Which is close to the old one, close to the known one. Whether there are fixed points farther out, that's extremely difficult to say. And in fact, usually this perturbation theory that you do to get there is not convergent. Okay, in general, this is always an asymptotic series, just like it is, for example, in QED, if you compute QED corrections in powers of alpha prime, of alpha, this is not a convergent series. In fact, it's known to be divergent. So this is what we're going to do. So actually, I heard this joke in a context which is in fact this context, amazingly enough. This was, just to tell you how old I am, this is in 1979, and it's in graduate school. And 1979 happens to be the 100th anniversary of the birth of Albert Einstein. So there was a big, conference in Princeton at the Institute. And so Steve Weinberg spoke there, and in fact told this joke, and he told it in the context of the renormalization renormalization group, because what he was working on is gravity, general relativity in 2 plus epsilon dimensions. And the idea is that in 2 dimensions there is no gravity, there's no graviton. So you go a little bit away from that, and then you try to find a fixed point there, which didn't actually work, but that's what he was talking about. And he told that joke, I still remember. I actually think it's a fairly profound joke in a way. So I'm going to begin with setting up perturbation theory or discussing it around free field theory, but then in fact we will very quickly generalize it to perturbation theory around any known field theory. Now, if you look under this section in Cardar, maybe I should say this on. But if you look at this section on Cardar, it's incredibly complicated and needlessly heavy. So, on the other hand, if you look at Cardy's little book, then things are much simpler, so I'm going to immediately follow that. So, there is one fixed point that we know if we're just dealing with a single scalar field, and I'm going to denote fixed point Hamiltonians with a star in general, and that is the model kappa over 2, the x, and then the gradient of m to the square. And this is also often rewritten simply as a half ddx of the gradient of phi square, where the root of kappa times m is phi, so we don't need to trail this normalization constant in front of it. And this Hamiltonian in any dimension we had shown was in fact a fixed point of the renormalization group flow if you started from a Gaussian theory. Okay. So another way of saying that is in fact this this Hamiltonian is invariant under scale transformations. So under the scale transformations, well basically x goes to lambda x, and then phi of lambda x is equal in general to some power lambda to the minus delta of phi of x. And then in this case, you can actually determine what this delta is. The dimension of the field is given by d minus 2 over 2. You can see that if you take that value, then in fact this Hamiltonian is exactly scale invariant. And if it's scale invariant classically, well, that doesn't necessarily mean it's scale invariant quantum mechanically, because you could have an anomaly. But when you have free field theory, then classical scale invariance goes over into quantum scale invariance. So classically scale invariant plus free field theory implies that it is quantum scale invariant. Okay. Okay. So now this is the invariant Hamiltonian. So now what we think of doing is, so if you wish, this Hamiltonian is a star. And now we're interested in parameterizing theories in the neighborhood of this Hamiltonian. So how do we do that? Well, how do we do that?
Deform it.
You deform it. And how do you deform it?
You add something small.
Yes, you add things that are small, and where do you add them and what do you add?
Sorry, are we still in the Gaussian model or not?
No, I mean, remember that, well, no, I want to be general now. It's true that this is the fixed point Hamiltonian in the Gaussian model. If we wanted to add things that restore the Gaussian model, you would add things here that are quadratic in phi. That would be one possibility.
You mean the small things that are quadratic?
Yes, so basically one thing that you might have is, for example, you have h star to begin with, and then I have d to the dx of the equivalent here would be, for example, phi square, and there would be some coupling to that, let's call it lambda 2, right? That would still be Gaussian. We could have many other things.
Couldn't you just add whatever you want, really? Can you just add whatever you want?
Well, you know, throughout we've always insisted on having local interactions. So we're going to insist on local interactions. And then also we've insisted on having translation invariant things and rotation invariant things. So basically these are the criteria. So we have the criteria, which is that we add local perturbations and also invariant under translations and rotations. I'm sort of doing this Euclidean, right? So you can do this also in Minkowski metric, but Euclidean here. So these are the criteria. And so in particular, I can add lambda 2 phi 2. I can add lambda 3 phi 3. I can add lambda 4 phi 4. These are all local, right? So clearly I can continue like this. I can also add the stuff that was relevant in the Gaussian model. For example, lambda square phi to the square, call that, let's say, u2. And so on and so forth. In other words, what I'm doing is basically add operators which are local and which are polynomial in the field. But I can, in principle, add an arbitrary number of them. And so even this, you know, this idea that it has to be polynomial is not fundamental. In fact, we'll see later on when we do the Coulomb gas that these operators do not need to be polynomial. But they probably need to be analytical. It's very difficult to do business when the functions are not analytic functions, because then you can't Taylor expand. So in general, I would say local and then also real analytic. But there can be arbitrary numbers of derivatives and so on and so forth. Okay, so that's what I mean. So now what do I mean by perturbation? That this thing is a perturbation. Well, remember, I already said that when we go out in this neighborhood of this known fixed point and do perturbation theory, in general, that perturbation theory is not convergent. It's not it's just asymptotic. So what we mean by perturbative is that formally, right, the lambda i's are, let's say, in absolute value much less than 1. The mu's i's are much less than 1 in dimensionless units. All of these things have dimensions, so probably what you mean is that if you express this in terms of the length scale of the microscopic physics, then these perturbations are small. So that's pretty much the name of the game. This is for perturbations around the free theory. And now, in fact, a way to organize these is that, well, the original Hamiltonian H star was scale invariant. And so we have seen here that the field phi, the dimension of the field phi, was delta, namely d minus 2 over 2. And since this is free field theory, I can actually, with respect to H star, I can calculate the dimensions of operators. Because in free field theory, there is no, you just look at what the operator is. So for example, the dimension of phi to the n is just equal to n times delta. The dimension of, a certain number of derivatives, let's say d to the k phi to the n, where what I mean by this is that, they can be in all possible arrangements. It is going to be k plus n times delta, and so on and so forth. So in fact, each of the operators that I wrote down, each of the local operators, in fact, had a definite dimension with respect to the free Hamiltonian. If I had written down something like e to the phi, that actually does not have a definite dimension. Okay, so the convention is going to be that the perturbation theory is simple, provided I organize it by perturbing with operators that have a fixed dimension with respect to the original Hamiltonian. And I can do that because the Hamiltonian H star is scaling invariant. So with respect to scaling, I can basically diagonalize the matrix of the scale transformation of all the operators that I have and work with the eigenvectors of that matrix. Any questions? Does that make sense? So needless to say that, except for these little properties here, this is really the most general thing I can write down. So I'm going to be, in fact, quite general with this.
Can I actually ask a question?
Yeah.
I think this is something I neglected when I first learned about this stuff. What you were just saying about with respect to the original Hamiltonian. So the way I understand what you just said is that we've defined an action of a multiplicative group, basically, on the space of fields. And we've demonstrated that the original Hamiltonian exhibits invariance under this action. And now we're saying, even when we go to a more complicated Hamiltonian, let's consider the same action of scaling on the fields. And we can now, with respect to that scaling definition, determine what the scaling dimensions are of the different operators. And that's what we mean by with respect to the original.
Yes. Right, because if I could rephrase, okay, let's suppose that these constants are non-zero here, the lambdas, right? So now I have a new Hamiltonian. Now I can ask, what is the dimension of each of these fields with respect to the new Hamiltonian? Well, that's different. That's not, I can't calculate that. That's going to depend on lambda. And the other thing is that with respect to that Hamiltonian, maybe some of these operators mix in dimensions. They may actually, mix with one another. So I can only ask that question reasonably with respect to a given Hamiltonian, or of course you can equivalently say a given transformation law. But it's only for free fields that this transformation law will apply the transformation law for phi to the n and for the other operators. If you have an interacting theory, that's not true. Each operator by itself has its own renormalization, multiplicative renormalization factor.
So the notion of dimensions being defined with respect to a particular Hamiltonian depends on being able to associate basically this scaling action with that Hamiltonian and have it be invariant.
Yes, that's right. With yes, I mean, you can, of course, you could imagine having a transformation, a scaling transformation on the fields under which H is not invariant. Okay, you can do that. It's not as useful. Okay.
Wait, so the scaling that we're doing there on the phi, is that lambda dimensionful or dimensionless?
No, lambda is just a number. Lambda is just a real number. 2, 3, 4. So it says if I evaluate the field on a real rescaled x, that's equal to the whole field, but up to a factor.
I guess I'm confused why it seems like the dimensions depend on the Hamiltonian or something like that.
Yes. They don't have to, but it's simplest if the scale transformation is such that it leaves the Hamiltonian invariant. If it doesn't leave the transformation, the Hamiltonian, I can go into more detail, but it would take me a little bit of field. If you have a Hamiltonian that transforms under scaling, then the relations are much more complicated. Okay. So it's when the Hamiltonian is invariant, then you have the simplest transformation, simplest Ward identity, simplest transformation.
Actually, something that occurs to me now that you brought this up too also is it possible, or are there cases where there exist multiple representations of this group of scalings on the Hamiltonian that leave it invariant? Or is there usually a unique one? Because then in that case you could define multiple notions of dimension, I would think, for a given theory. I don't know of any examples, but.
Right. I suspect if you say it that generally, you probably do have possibilities of, but whether that's useful or not. Well, I think maybe the best way to say it is that the answer to that is no.
Mm-hmm.
And the reason is the following. Suppose I have two different transformations. If there are different transformations on the Hamiltonian, there has to also be different transformations on the fields themselves. But now you can see that if you have two different ones, let's say with different dimensions, then basically the action of their ratio is an internal symmetry, right? Because one transforms x to lambda x, but then I can use the other one to go back. Mm-hmm. And then the ratio between these two is an internal symmetry. So I'd rather say that there's really a unique scale invariance, but then you may have other internal symmetries.
I see.
I think that's probably a better way of organizing it. Other questions? Okay, so now in fact it's very, it's useful in particular to define what we mean by perturbative, to write this Hamiltonian in a somewhat different way and bring out explicitly the microscopic scale. So what I mean by that is I know, let me just do this for example, for the operators d to the d x of phi of x to the n. So now I see that this operator has dimension, first of all, from the d to the dx. That's a minus d. I'm counting in dimensions of inverse length. And then phi of x to the n is n, and then delta is d minus 2 over 2. So this is the dimension of this operator. And so if I want to have dimensionless coupling constants, then it makes sense to write this expansion in a slightly different way, which is to have a sum over n, let's say, in this case, and then have a dimensionless coupling Gn. And then I will put in a factor of the microscopic length, A is, let's say, the lattice spacing. Exactly to the dimension that compensates for the dimension of the operator. So A to the minus d plus n, d minus 2 over 2. And then times d to the dx of 5x to the n. Okay, so that means that, so now this whole combination, this has dimension 0. And so also this has dimension 0. And remember, H star, the transformation law of phi, was chosen, the dimension of phi was chosen so that the Hamiltonian H star is dimensionless. Okay, that's why it's invariant under scaling. Okay, so I can do that because every operator I use to perturb has a definite dimension. If it didn't, then I don't know how to do this. Okay. But, so is this, are you all with me?
There's a minus sign there?
No, because this is a length, actually. And I computed here in dimensions
Oh, that's the
of inverse. Like, yeah, sorry, that's the way, you know. A particle physicist always computes in dimensions of mass, right, of length. Okay, so this is, and now of course I've only included there the operators phi to the m, but it doesn't take long to imagine that I just can include also other operators with derivatives and so on and so forth. I haven't written it down, but you can imagine that we do that. Okay, so in fact now from, yes, and then I should also say that here we have these integrations, but the presence of this lattice spacing, A, functions as setting a scale for the perturbation, but also A is a UV cutoff. So in particular, it doesn't make sense with a UV cutoff, it doesn't really make sense to explore the physics at distances smaller than A. So for example, if we have two operators, let's say phi to the n of x and phi to the n of y, right? Then these operators are in a sense, this is well defined only if x minus y is larger or equal to A. If I ask what these operators do at distances smaller than it, I really don't know, because that's part of the microphysics. So in particular, if we have, for example, double integrals here, then the difference will be cut off by this, otherwise I don't know what I'm doing. Okay, so now I formulated this for the free theory, but in fact you see that there isn't anything all that special about the free field theory, so I'm now going to sort of in one sweep generalize it to any theory that's invariant. So generalization to arbitrary scale invariant A star. So I'm now going to ask you to imagine that A star is invariant under scale transformations.
When we make the scale transformation, does that change the UV cutoff, or?
Yes, we're going to come to that. Yes, so, right. So in the free field theory, okay, the dimensions of the operators are simply given by this so-called naive, or sometimes called engineering dimension counting. But of course, as soon as you have interactions, that's no longer going to be true, because in particular, you will now have operators, you know, close together at short distance. Okay, so in the interacting theory, it will no longer be true that you have scale invariance in the same way, because in fact of these cutoffs, and that's exactly what we want to compute. That's exactly what the beta function is, in fact. So I'm going to assume that we have a Hamiltonian like that. Now I'm not going to write it down because I want it to be general. Okay, if it's general, it's too general to write it down. However, I'm going to assume that in some sense I know, so we assume that we know all the local operators in the theory And we have these local operators, a whole bunch of them, and I can now basically say with the same argument that I used for free field theory, I have this scale transformation that leaves a star invariant. I can ask, under that scale transformation, how do these operators transform? In general, that's a complicated thing, but the scale transformation is a self-adjoint operator, so it can be diagonalized. And so that means that there is a basis. We know all operators. There is a basis in which, so a basis of operators in which the scale transformation, usually called D, by the way, is diagonal. So, and so that means that if I call these operators phi I, then each operator has a definite dimension, which we're going to call delta I, or phi I. So if you want to be more formal, right, this is a finite scale transformation. If you want to write that as a unitary transformation in Hilbert space, you would write something like e to the lambda, e to the log lambda times d phi at x, e to the minus log lambda times d. Maybe with an I. Okay, it would be like time evolution, but now it's scale evolution, and then d would be the self-adjoint operator representing dilations. And so we also have, for example, that d with a star is equal to 0. Are you all with me? Does that make sense?
Confused why the log is there, I guess, but.
Well, because it's in the exponential, so to recover the right
I think I see it.
to recover the right thing, I think there's a log. In some sense, if you wish, you can write this as e to this times the log. Okay, and then delta I is the eigenvalue of b. That's how you recover that. Now restore it to the original notation. So does this make sense to you? So the previous case falls into this case, where the phi I were simply, for example, the nth powers of phi, but then also combinations of phi and an arbitrary number of derivatives. That would be basically all the operators of the theory. So now we can do the same thing. So the perturbed Hamiltonian H is now the original H star, and then plus now we do exactly the same thing. We sum over all I, and then we put in a dimensionless coupling GI to make this coupling dimensionless when coupled to the operator phi I need to put in the thing that compensates the dimension, and that is d minus delta I. Oh, sorry, the other way around. Delta I minus d. Because this has dimension this has dimension minus d, this has dimension d. And so that,
Are the phi i's the elements of the basis, or just a list of all of them? All of them?
this, yeah, phi I is, when I say basis, I don't mean orthogonal or in any sense, right? Just a basis, a linear, a basis for the linear space of all operators. So it's a list in a sense. Okay, so here again, this has been set up in such a way that this has dimension 0, the couplings GI have dimension 0, and the Hamiltonian H star has dimension 0 by that equation. And so, so with respect to this dilation generator that we use with H star, then H is invariant.
Sorry, I missed the part. Why are we not considering powers of phi i's?
Because my list of phi I includes everybody. Okay, so
Phi
phi I,
squares.
so this includes phi to the n, and then some, all possible combinations of these. Okay, so I'm using just a single index running through all possible operators. Because in the general formulation, there's nothing all that different between this kind of operator and that operator, so I have to treat them sort of all democratically. Okay, so this is the perturbed Hamiltonian, and so now what we want to do is actually, so far I've not talked at all about renormalization group. So in particular, what we're going to be interested in is compute perturbatively objects like, for example, the partition function z, which is the trace of e to the minus beta h. Okay. Now, for all practical purposes for us, temperature really does not play much of a role, so I'm going to just set beta equal to 1, right, along with h bar c and everything else. It doesn't really matter. You can just restore. You can absorb it in this kappa that I set to 1, or absorb it into the coupling.
Isn't it already absorbed in H since H is unitless?
I made it dimensionless, so from that point of view, I've already, in a sense, absorbed the temperature in there. You can just reabsorb it into a redefinition of the fields, and so it's not a big deal. So that's one thing we would like to compute, or actually more generally, we may be interested in computing Z as to compute the thermal average of some operator O, which is the trace of O times e to the minus h divided by Z. And this operator need not even be local. It could be the product of phi I at x and phi j at y or something like that. So that's the kind of thing we're interested in computing. And so we want to, we're going to not compute this exactly because we can't, but we will want to compute this perturbatively. So that means we expand in powers of phi. And so let me, for example, look at the expectation value. Well, let me not look at that. That's more complicated. Let me look at the trace of an operator times e to the minus h. In Cardi actually looks at the partition function, but that argument isn't entirely, it's a little bit too specialized. I'll tell you why in a second. So what is this? Well, we would expand in powers of g. So the leading order is trace of O e to the minus h star. The next order is minus the sum over I of gi a to the power delta I minus d of the trace of phi I, I need an integral, dx of the trace of phi I of x e to the minus h star plus a half sum over I and j, gi, gj, a to the delta I plus delta j minus 2d, d dx.
There's still the operator in the trace.
Yes, thank you. Yes. Double integral, and then the trace of O phi I of x1, phi j of x2, e to the minus h star. And of course I could go on, but I'm not going to because this will be all we need. So it's a formal expansion, and in general not convergent. Okay. And now let's introduce the notation that that the expectation value of O star is 1 over Z star trace of O e to the minus H star, where Z star is equal to the trace of e to the minus H star. In other words, what I want to introduce a notation is the terminal expectation value of operators computed with respect to the fixed point theory. In principle, like when it is free field theory, I really know how to do that. We will see later on how to do that in practice. But if the theory, let's suppose the theory H stars is well known, so then the assumption is that you actually would be able to compute out these terminal expectation values. So in that language, we can rephrase this equation in that language. And so we would then have so I'm going to divide the trace of O e to the minus h. I'm going to divide it by Z star. And so the first thing I find there is the expectation value of O star. And then the next one is minus sum over I, di, a to the delta I minus d. I don't need more space. Expectation value of O is phi I of x star. And then plus, I'll just continue on this line here since I'm doing this way. Delta I plus delta d, double integral. And then the expectation value of O, phi of x1, phi of x2, and so on and so forth, with a star. Okay? So each of these, in fact requires typically some, I haven't exactly said what O is. O is generic, we're going to ignore any singularity that may arise when X approaches O. But what we're not going to ignore is the singularities that arise when X1 and X2, oops, they should be I and J, that arise when X1 and X2 come close to one another. So in fact, the integral here really should be considered when X1 minus X2 is larger or equal to A. Are you all with me? Okay, so then since this is a natural breaking point, let's take a 5-minute break, and then we'll see how to handle this sketch.
How do you do the expansion again?
Remember that, right, e to the minus h, and h was a sum of all these terms. So h is h star, right, plus sum over gi, phi I, a factors. So you basically expand the exponential. I'm thinking of this really in terms of functional integrals. I'm not thinking so much in terms of operators. I mean, they are operators, but I'm thinking of evaluating this in the functional integral. So the ordering of the operators does not really matter. Okay. But otherwise, you're just expanding the exponential. So the first term is just a linear term. And then the second term is a half, right, in the exponential. And then is the product of two of these terms, which I write as a sum with two indices.
This is the whole No, this is just different.
Okay, so let's take a little break.
This was actually from before. Yeah. I used it for a GRE prep class too. So.
Do prep classes do your stuff?
Hmm?
There's no really UCLA. That's private stuff.
The GRE prep class? No, it was for UCLA for like this last summer and the summer before that.
But they hired you.
Yeah. It's pretty good.
I have all my nails still from the beginning.
Oh, really?
I'll do mine.
I just wanted to.
No.
Couple days, like, I mean, I'll take a month for like 2 or 3, and then I got past like 1.5.
Some sweaty guy in the
You don't mind making more.
The denominator?
Like you said, we're going to worry about the next one for each other in the second.
But we're gonna worry about.
When X1 and X2 are close together, and then we have it for the second, the third term there.
We're not gonna,
I
well,
said we are going to worry about it. Then why don't we worry about when O, or the place that O acts is close to X in there?
think he might have said that backwards. I'm not sure. Because he said we weren't going to worry about when x1 and x2 are close, but we're not really, right? Because
Yeah. Wow.
I mean, I understand why we're not looking when x1 and x2 are close. And then, so now the question is, why would we worry about when the operator is close to x, you're saying?
Yeah. Maybe is it not local?
Yeah, he said O could be anything
Oh.
right now.
Yeah. So is O? It's not necessarily a local operator, it's just an operator.
Yeah, it doesn't really have to be. I mean, the reason Cardi basically just says O to 1, briefing from the partition function, right? But now, these operators are going to have dimension here. So if you have no O here, this expectation value is 0 unless the operator is the identity. But then you will want to make an argument generally on that matrix element, so you can't really do that. I mean, it's a bit of a shortcut, but I think this is actually okay. So you could make O, anything really. Could be a local operator. The other thing you can do is actually just insert this between two states, two definite states. That's another possibility.
And then O is a projection operator.
Or a projection operator, exactly, that's right.
But if O was local, you would have to worry about when the place it acted got close to X.
You would, that's right. I mean, there would be additional terms that come from O, but suppose, for example, that we put O far away, or something like that.
Why are
Or
we
you can also simply say, don't look at the singularity whose, support is given by O. With more work, you just insert an operator 5K, but then you would have to work out exactly what all the things. But it's completely possible with more work.
Why are we dividing by set star? I'm not so sure we
Z star is just the partition function for the scale invariant operator.
Right, but if we want to compute the expectation value of O, shouldn't we divide by set and also expand to 1 over set?
But this is always, I've always listed in here the expectation value star. So it's always calculated in the fixed point theory.
Right, but what we're trying to compute is the expectation value of O without the star, right?
Well, actually,
Isn't that the objective of this computation?
yes and no. We're never going to compute this. We're going to perform a renormalization group transformation on it and see what the flow of the couplings is.
Okay, I guess my question is, the last two terms
Mm-hmm.
come from correct expanding e to the minus h in this trace. But this is divided by the trace of e to the minus h.
Yes.
So, I mean, you only wrote the trace of e to the minus h star, but there will be other terms coming from expanding this 1 over set.
Right. So in other words, as we said, this is not the expectation value of O.
Right.
That's right. It's in fact the expectation. You could write this as the expectation value of O times Z over Z star.
Exactly. Okay.
It's not what I did in the notes, but so I think I'll land on my feet again.
I thought we were after computing the expectation value.
Well,
Close enough.
close enough. Okay, thank you. I think if I divide it simply by Z, then the ratio Z over Z star, I can expand in this way, and I would just have the identity inserted.
Yeah.
Right. So that's an alternative way of doing it. I could actually do that. It's more work, right?
Yeah.
But it can be done. Yes. Okay, So, what we're going to be after is performing a renormalization group transformation. Now, before I do that, however, I need one more tool. So the next thing we will do here is perform an RG transformation. But I need, first of all, one more tool. And the tool is called the operator product expression. Or also just abbreviated, the OPE. So what is the idea? Well, I've made a list of all my operators. And now suppose that I have the product of two operators. So this is the product in Hilbert space, really. Okay. Now, the operator product expansion basically consists in having an expansion when the distance between x and y is small, or at least I'll expand in that distance. If phi I and phi j were ordinary functions, you would know how to do that. That's called Taylor expanding. Okay. So if we were Taylor expanding, we would say then that you can, for example, write phi I of x as equal to phi I of y, and then you would have an infinite series from 1 to infinity of x minus y to the power n over n factorial, right? And then the n is a derivative of phi I at the point y. And I'm sort of ignoring that we're in perhaps many, more than one dimension here. But so that would be the formal expansion. That's, just an ordinary Taylor expansion. And now, of course, things are a little bit more tricky when you do this with operators, because when you place, local operators at the same point, there are divergences and so on and so forth. However, our assumption was that phi I gave us a basis for all the local operators in the theory. So if you can perform such an expansion, then it suffices to sum over the contribution from all the operators in the theory, and that must be it, because by definition, I've listed all the operators in the theory that are local as phi I. So to summarize, the OPE is an expression that gives a formula for this product as a sum over all operators phi, and then these operators phi k could be evaluated at y or could be evaluated at the midpoint. It doesn't really matter, but it is somehow sometimes nice to evaluate at the midpoint. And then you have coefficients which depends on I and on j. They depend on what the operators are. And they, of course, depend on what the operator is that comes in here. And then, finally, this depends only on the distance. And this object C, this is a C number. This is, in general, a real or a complex function. Okay? And this equation is to be understood not so much purely as an operator equation, but actually as valid when inserted between any two states in the Hilbert space, or more generally inserted into any correlator. So in particular then, if you had, for example, phi I of x, phi j of y, and phi L of LC, okay, then this would be equal to the sum over k, Cij of x minus y times the expectation value of phi k of x plus y over 2 times phi LZ. And this would be true for all phi L, sorry, and all z. And whatever that correlator is, these functions C are independent of the operator phi L. That's the meaning of this equation. Does that make sense? Okay. Now, you know, there are slight complications to this. For example, I'm acting here as if the operators phi I and phi j and phi k are all scalar operators, but they need not be. For example, I could have simply the derivative of a fundamental field. This would be the vector operator. So when you have that, then these functions, these things are called coefficient functions, are actually tensors in position space, okay, which depend on x minus y, and then this can also be a tensor and so on and so forth. So the formula is more complicated, but anything that I'm going to say it will be unchanged. So this is the operator product expansion, and this is an extremely powerful thing to have, as we will, for example, see in this calculation here. Are you all with me?
Is there like a straightforward way to find out what those Cijks are?
You have to compute this and you have to compute that. And in general, it's a pain in the butt. Okay. So, in fact, that's a very good question because there is one more thing I wanted to say here, and that is if you have to compute these coefficient functions in general, this is complicated. Okay. Always complicated. And in particular, if you did this, for example, in QCD or in the weak interactions or something like that, then the C's have dependencies on x minus y, but they depend on the renormalization scale, and they depend on how you introduce the photon, the gluon renormalization prescription, and so on and so forth. So in general, these things are very complicated. However, if the phi's have definite dimension, and this is still all with respect to this fixed point Hamiltonian H star. So with respect to H star, then in fact you can see that we have a very big constraint on what these C's can be. Because if we transform, so we let x go to lambda x, and we let at the same time y go to lambda y, then we see that this has a definite transformation law, multiplicative, this does, and this does. So actually, this has a simple transformation law, okay, which you can easily solve for. So Cij k of x minus y scales like x minus y, and we can now compute this. So the dimension here, if we count actually dimensions in terms of length, the dimension here is minus delta I, minus delta j, and minus delta k. And that means that Cijk behaves like delta k minus delta I minus delta j. We just checked that I did my algebra. Right. Now, as I said before, this is only the overall scaling behavior of this function. If there are vectors and tensors involved, then some of these powers are actually represented by x minus y to the mu and some, component mu and so on and so forth. So we're not really going to need that here, so I'm going to ignore it. But what is important is that the only thing left over, once you've extracted the dependence on x minus y, is just a constant. And I think I call that Lagrange thing. So these are now independent of x and y. So, in general, the OPE is complicated to compute. You compute it in perturbation theory, okay? But in the case of when you have a scale invariant theory, or when you're considering the OPE with respect to a scale invariant Hamiltonian, then in fact the space dependence of these C's is essentially unique up to a constant. Yes?
I'm confused about when an operator wouldn't have a definite dimension with respect to H star.
When H star is a scale invariant Hamiltonian?
Mm-hmm.
Right. Well, for example, if you have, just e to the phi, right, that does not have a definite dimension because
Oh, okay.
you would have phi and phi squared and phi cubed and so on and so forth. So it
What is
more or less has to be.
I mean, does that operator even make sense then? I guess that operator wouldn't even make sense to me. It's like.
Well, we'll see a little bit when we do the cooled gas and the XY model. We will have that operator. You will see that you can make sense out of it in some cases.
Couldn't you just take something simpler, like different polynomial
Yeah, phi squared
powers?
plus 1,
Yeah.
let's say. That would not have a definite dimension. Of course, you can nicely separate it into the sum of two things that do have a definite dimension, as you could with the exponential. The fact that we work with this basis of operators of definite dimension is an organizational convenience. Okay, it's not necessary, but if you do that, then things become much simpler and well organized. And the whole idea of this kind of stuff is to be well organized.
Are there conditions under which there exists a basis for operators consisting of operators that each have a definite dimension? Is that possible usually, or?
Well, let's see. I'm sorry, can you say that again?
Yeah, so are there situations, or maybe it's generally true, I don't know, that the basis of operators that we chose in the beginning consists of a list of operators, each of which has a definite scaling dimension with respect to the original?
Right, okay. Well, think of the symmetry generator is D, right? The operator of dilations is D. It's a self-adjoint operator, okay? It has to be by the construction. So that means that its eigenvalues, let's see. Well, if you have a unitary theory, right, then D is Hermitian, is self-adjoint, and then you know it's diagonalizable, right, in the basis where, okay. So then I think there always exists the basis of operators, right? With
Just the projectors corresponding?
Yeah, that's right. You just have the projectors corresponding to each dimension. There may be a finite number of operators there, but then you can diagonalize that if you want, or you just have different operators with the same dimension. If you have a theory which is not unitary, then D does not have to be self-adjoint. Then it's not necessarily the diagonalizable matrix in the standard sense, but any matrix. So the obstruction to that is if you have spaces with different eigenvalues, they're block decompose. But within a space of a given eigenvalue, you may not be able to diagonalize. Okay, that's the Jordan, normal form, right? What that means is that you can have an operator which under a scale transformation transforms like lambda to the minus delta phi of x, but with an addition. And I don't remember, I think it's actually lambda to the minus delta log lambda times another operator. This is actually the representation simply of a matrix which has the same dimension eigenvalue 0 on the diagonal, delta on the diagonal, has a 0 off diagonally here, but has a 1 essentially here. That's the Jordan normal form. This 1 is responsible for mixing the operator with another operator. But you can really have that only in a non-unitary theory. Other questions? Okay, so now in fact it turns out that with the help of this OPE tool, we're going to be able to carry out the renormalization group transformation and repackage the information we get in a very economical way. So let me show you how that works. I think first of all I have to remind you how you do a renormalization group transformation, right? So what did we do again? Well, we have A is a UV cutoff. So remember that under the renormalization group transformation, you basically enlarge A. You send A to a factor B times A, where B is larger than 1. This is equivalent, right, when we consider the momentum cutoff, which is like 1 over A, and then we let lambda go into lambda divided by B. We made the momentum cutoff smaller, and that's equivalent to making the UV length cutoff larger. Okay, so that's the transformation we want to do. And it's actually convenient to write this infinitesimally. So we'll write B as 1 plus delta L. So now when I do that, so I want to perform this on this expectation value. So I'm changing A, so the question is, where does the A appear?
Why does the RG transformation have to be small?
Doesn't have to be.
So what is delta L actually? Is it a small?
Delta L is small.
So why does it have to be small?
It's convenient. I want to get the differential equation, right? I can do.
But later you're going to make it continuous.
Yes, you can integrate it, right? So you want to find out the effect under an infinitesimal change of scale, and then once you have that, you can integrate it. So where does A enter? Well, I left the formula on the board here, so it's sort of obvious that first of all, A enters in these factors of A delta I minus D in each of these factors. Then A also enters as a cutoff. X1 minus X2 is larger than A. If I vary A, then I vary that cutoff. And that has an effect. And finally, the whole system, remember this is after all a thermodynamic system, the whole system has, let's say, length L, so there is a dimensionless way of characterizing L, which enters in this way, for example, the total length of the system. Now, why do we consider infinitesimal scale transformations? For infinitesimal delta L, these three effects just add up without mixing. If I did this on a finite transformation, there's an A here, but then the cutoff also enters here. So if I did this as a finite transformation, then these things mix. And that's not so easy. But when I do it infinitesimally, then everything is linearized and enters in this expression in the first order. Okay. So now, what is it that we want to, what do we want? What do we want to know? Well, when we did the Ising model, what is it that we wanted to know? What we wanted to know was if I make a change in scale in the Ising model by integrating out some of the degrees of freedom, I made the lattice scale larger, then the question was, how do the couplings in the theory have to change so that the physics is actually the same? Okay, so that, for example, if we were computing the partition function, so that the partition function of the original theory is the same as after I've made the renormalization group transformation. Here, we're enlarging that a bit by including this operator O for reasons that I had explained a bit before. So what we want is we want to know how the GI have to change in order to maintain the same quantity, basically expectation value modulo Elliott's worries about the difference between what I wrote down and that actual formula. So that's what we want. It's always good to know what you have and what you want, and then now we want to know how we're going to get there. So it's convenient, the fact that these three different effects can be simply added up when we make an infinitesimal transformation is particularly convenient because it means that we can change the coupling for each of them independently. Let's look at these three effects now. So the first effect, we let A go to A times 1 plus delta L. So that means that A to the delta I minus D goes into A to the delta I minus D. 1 plus delta times delta L times delta I minus D. This is not too hard.
Can I just say something?
Yes.
It might be really stupid, but when, the first time we did RG flow, we said that what we wanted to keep fixed was the partition function, and we. Okay, so do I have to understand that actually the definition of RG flow is that it keeps all the expectation values of all operators, one of them, of course, the trivial one, the same, and that's why we're leaving the expectation value of O invariant.
Yeah. No, actually, that's not really what we want here, because the operator O in general will have its own transformation law, right? If it's an operator of definite dimension,
right,
then it wouldn't be invariant, but it would transform according to its, canonical dimension, right? So.
So then why do we keep it the same?
You'll see in a second.
Oh, yeah.
I could, of course, never have mentioned, this slight inaccuracy of Carter and truth Barcelona of the rock. I don't like to do that. So I'd rather complicate it a little bit and share honestly what the issue is, and then in the end say, it's not really a problem. So in general, this kind of expectation value of O has a dimension, which it will have in the unitary theory if it's not the identity operator. Then it's not true that that this thing should be invariant, but it should transform like O. But O transforms the same way in each of these things because it enters linearly. So I'm going to ignore the short distance issues with O, and when I do that, then O is just there as a place setter. You could maybe more easily think of inserting, inserting two external states, and then there are no singularities if it's a regular state. That would be perhaps needed. In the next incarnation of this, I'll improve it. Okay. All right. So now, I have this transformation sitting in here, and now the question is there a way to change the G's so that that's compensated? Can I do that? Let's say, can I do it in the first term? And then we can ask whether we can do it in the second term.
Just with minus.
Yeah, it's completely trivial, right? In a sense, the only thing you need is that this combination be invariant, and that immediately tells you that GI should go into GI 1 minus delta L times delta I minus D. So, in other words, the change that I need to introduce in G is just minus GI times delta L times delta I minus D. That was not too bad. Okay. Now, let me do number 3 first. The physical size of the system you keep fixed, because otherwise you're not doing anything. Otherwise you're just calling a meter an inch essentially, and it doesn't make any change. So L is invariant. So in fact, I don't need to do anything there. L is simply invariant. So then comes the last part, and that's of course a non-trivial part. So that's item number 2. And let me do that out here.
Where does L explicitly come into this anyways?
Well, it's coming in basically because I'm doing these integrals over all of space, okay? And as we will see in just about a second, some of these integrals are not necessarily convergent when L is infinite, so you really need to keep the L there. Okay, so now let's do the last part. So the last part is the part due to the fact that we have a cutoff. And if we change A, then we change what this cutoff is. So this is point 2. So we have these two integrals with the condition that x1 minus x2 is larger than A. And then we have phi I of x1, phi j of x2. Okay. And now we change, so this is changed to d to the dx1, d to the dx2 of the same thing. Except that now x1 minus x2 is larger than A times 1 plus delta L. So, what is this object? Well, this is in fact equal to the original thing. Let's rewrite it. change. So the change is in fact the integral dx1 dx2 of O phi I of x1, phi j of x2. And now we integrate the difference here. So in fact, x1 minus x2 should be between A and A1 plus delta L. And even the sign is right, because this is a larger, no, let me check that the sign is right, sorry. This is a small domain of integration, so actually the sign has to be minus. Are you all with me? Now, seems like now we need to do something, right? We haven't really done much so far. So if there were no singularities, when x1 and x2 come close to one another, then this region is just a shell of distance A times delta L. So if A is very small, then you would think this does not contribute. But it does contribute because, in fact, when you take two operators close together, then there are singularities. How do we evaluate this contribution?
The OPE.
Right, there's one piece of information that hasn't been used, right? It's like in the Hitchcock movie, there was a hat hanging there, so that hat has to be used at some point. So indeed, now we can in fact evaluate this with the help of the OP. Just remember what the contribution was from number one. I'll erase it here. So now we're going to use the OP and evaluate this contribution. So let me just rewrite the expression for the OP. So the OP tells us that O with phi I of x1, phi j of x2 is equal to a sum over k. Then we have these constants, lambda I, j, k, divided by x1 minus x2 to the delta I plus delta j minus delta k. And then times phi k at x1 plus x2 over 2. That's what the OP tells us. So in other words, what I need to evaluate is the integral d dx1 d dx2 of 1 over x1 minus x2 to the delta I plus delta j minus delta k times O with phi k of x1 plus x2 over 2. Okay, that's what I should do.
Sum over k.
Well, yes, ultimately there will be a sum over k, but I'm going to worry about the integral first. How would I think of doing this kind of integral? And of course, yes, I should have said here that I should have said that A is less than. So how do I do this kind of integral?
Isn't it kind of like a delta function almost?
Mm-hmm.
Do you want to change to like relative coordinates?
Mm-hmm. So, well, in fact, that's why I have used this particular form of the OP. Could have been another one. Let me introduce x1 plus x2 over 2 and call that v, and then call u x1 minus x2. As it turns out, with this factor of a half, it's actually true that d dx1, d dx2 is equal to d dv, d du without a factor. So that means that we can now write the integral as d of v, d of u, and then here I have 1 over u to the delta I plus delta j minus delta k. And then, let's say, yeah. And of course, u has to be between a and a plus a times delta L. And then here I just have O of phi k of v. Now actually you see that I wrote it sort of in a silly way. I should simply, these two integrals decouple from one another, and this is simply d dv. This doesn't depend on v, this doesn't depend on u. Okay. Now, there is no way we're going to carry out this integral, but we don't have to, because this integral is exactly of the type of the first order term. That's what the OPE does. The OPE takes two operators, merges them into another operator, but that operator was present here. So we're not going to be able to absorb the change in this term. We'll be able to absorb it in this term. Okay. And so now the rest is easily computed. So this basically, what is this integral? Well, this is an integral over a shell. Okay. So the size of u is actually equal to a. And then, so we can evaluate this integral without doing anything, which is my kind of favorite kind of integral. And so u actually, this gives me a to the minus delta I minus delta j plus delta k. And then I need to also take into account this d to the d, which gives me plus d. And then I will have delta L over A. Oh, sorry. Delta L. And then the only thing I've forgotten here is actually the volume of the unit sphere in d dimensions, so we'll call that SD. There is a formula for SD, but you won't really need it. I mean, it's some formula. Okay. And now, in fact, you see that what we have here as a prefactor, we have a to the delta I delta j minus 2d. This combines with a to the minus delta I minus delta j plus d. So that exactly becomes, in fact, delta k minus d, which is what we have here. That's no accident, because by construction this term is in fact scale invariant. And now we see how we can compensate that. We can compensate it by a change in GI. And so, okay, I think I can now just write down what that change is. So the change in GK is given by, first of all, there's this factor of SD. There is a factor of a half. Okay. Then from the OPE, I have a factor of lambda ijk. And then I have also the coupling constants GI, GJ. Well, and then I need to sum of these. I and J. And now we have to be careful to determine the sign. So So the sign here has been plus. The sign that we changed here was minus. But there is a minus sign out here. So to compensate, I need a minus sign. Now, if you did this for the term with 3 phi's, you can see what's going to happen. With the 3 phi's, okay, there will be pairwise exclusions because there will be now 3 x's, x1, x2, x3. So there's basically when x1 comes close to x2, it's one region, and x1 comes close to x3. And so you have each of these regions, you need to cut them out. For each of the cut out regions, you have a shell you need to integrate over, and you will use the OPE, okay, to do that. And so the effect will be that you can, when you've done that, then you can compensate again by part by the second order term and part by the first order term. So, it's not often that you really need the RG equation to higher order than this, but I'm just telling you how to do it. So now, in fact, we can write everything down. We can write down the final equation, which is that the way GK changes as a function of L is given by, so the first change was proportional to the coupling and to D minus delta K. And then the second one is minus a half SD. And then the sum over I and J of lambda I J K times G I Gj plus of order Gj. So what you see is, first of all, this RG equation is governed by the dimensions of the operators. Okay. And secondly, by these OBE coefficients. That's what goes in there. By the way, I have not made, for those of you who know, about conformal field theory, I have not assumed conformal invariance. I've only assumed scale invariance. The fact that these lambdas are constant as a result here of just scale invariance. I don't need conformal invariance. Never assumed them.
What's the difference?
The difference is a lot more symmetries. A conformal symmetry is a symmetry where all the angles are preserved by definition. Okay. So a scale transformation preserves all the angles, but there is one more transformation that we need to include, which is essentially the inversion. So x mu goes to x mu over x squared. And that transformation together with scale, rotation, and translations, that forms the conformal group. So it's a stronger condition, and I haven't assumed it here. So anyway, so this is the renormalization group equation. The powerful thing about it is I have not assumed what theory I was expanding about. This is generally true, as long as I'm expanding about a fixed point. Okay. So this is all abstract, but you see the derivation on the blackboard looks big, but actually it was a double triple derivation, really. And next time, we're going to see how to use this, first of all, around free field theory to get the Wilson-Fisher fixed point, but then also with operators that are not actually of this polynomial type, to do the XY model and the Poole. But it can all be done just with this formalism very simply. So.
I mean, it looks nice, but we still don't know what the lambdas are, so it's like...
Well, you've reduced one problem to another, right? But you will see that determining the lambdas, for example, in free field theories, is essentially an algebraic question. You don't need to do any real work. Other questions? So by the way, this is the derivative of g with respect to scale, either length or mass. That's called the beta function. So the right-hand side of this is what's called the beta function. Okay, this is a key element of the renormalization group equations. It is the function that describes how the couplings change with length or mass.
Are there examples where the exact RG equation is known besides situations in which you've solved everything about the theory? When you solve everything, you mean solve for all the correlation functions? Yeah.
So, right. Yeah. Well, there are several examples known. In some sense, the most important and canonical ones are supersymmetric Yang-Mills. So if you have, for example, n equals 4 super Yang-Mills, then the theory is just plain in the scaling theory, the beta function is 0, and yet we can't quite, completely solve it. Okay. The other case would be n equal 2 super Yang-Mills. In that case, the beta function is one loop exact, up to incidental corrections. But in perturbation theory, it's one loop exact. Okay. And so that means that these terms are, no, actually you have to count a little bit differently. It depends on how you count. In n equal 2 Yang-Mills, this term isn't there. And you have, because the coupling is dimensionless, so the operator, multiplying the coupling is the action. Okay. And that's dimension 4. So this term isn't there, and this term is exact. That's it. There are no higher terms except for incidental corrections. And the solution of Zyberg and Whitley was actually to calculate these incidental corrections using the properties of S-val. So that's a very famous example where actually the beta function is completely known. I'm sure there are some other cases. Actually, another important case is the Wesson-Meador model in 2 dimensions. There, again, the beta function is again one loop exact. None of the Lingchern-Simons is known, but it's quantized, so it's a little different. So there are a few. Usually supersymmetry is what guarantees that there are no corrections between one loop. And the reason is that this, after all, is related to the void identities of the stress sensor, right? Because the stress sensor gives you the dilation current. And so in supersymmetric theories, the stress sensor is in the same multiplet as a U1 current, the R symmetry current. And so then once I know the charges of that, then I know the anomaly of the current, and then I know exactly to one loop what the beta function is. So it's always related to the fact that, as far as I know, pretty much, that the stress tensor is in the same multiplet as the current, which is anomalous. And then the anomaly is always one loop for a current, for an internal current.
Okay, the only thing that sounds a little bit obscure to me is why we have chosen this object to be not changed by RG.
Well, yeah, as I said, Cardi basically just considers the partition function. Now, the problem with the partition function is that then if this operator isn't there, and this is a scaling operator, okay, its correlator, its expectation value is 0 unless it's the identity. So I really don't think you can sort of make that argument that this contribution can be absorbed in that if actually the thing is 0. So that's why I put this in. I think you can just perfectly well do this when you take for one of the operators phi k, and then you need to take into account the transformation law of that operator. But since it's perturbation theory, it's not. The only thing you compute is expectation values with the operator H star, and then like in free field theory, those are all just weak, contraction type things. So So I put it in order, I think, to avoid the issue that,
I see.
each of these correlators is actually 0. And I'm pretty, I know for a fact that having inserted this operator can be disentangled neatly
Okay.
from what I've done before.
I see.
The other thing you could do is actually take the partition function and go to one higher order.
So 2 and 3.
Yes, 2 and 3, and then those are not 0, and then the correction of 3 you would feed back into 2. But, the blackboard being sort of a finite length.
Yeah.
Right.
Okay, but the fact that one can also use just the partition function to show the
Yeah, you could, yes, yeah, that's right. Absolutely. Okay, so I'll see you next week.
So you get the same answer just using